Let's quickly recap the central limit theorem for proportions before we move into an application problem. So there are three conditions that we have to meet. One, it has to be a random sample with independence. And in order to ensure independence, sometimes if you're doing it without replacement, you have to make sure that your population size is at least 20 times the size of your sample. And then the other condition besides that is that it has to be normally distributed. And in order to ensure that, you have to have a large sample. In particular, n times p times 1 minus p has to be greater than or equal to 10. And if you remember, that condition comes out of chapter 6 with the binomial distribution, because everything with proportions is really based in that binomial probability theory that we learned in 6.2. So if you have these three conditions, then you have a distribution of sample proportions as follows. It's going to be normally distributed. It'll have a center of p, mu sub p hat equal to p, and a spread, which is the standard error of the proportion, which is equal to SE of p hat, which is equal to sigma sub p hat. Okay? And then there's that formula for it, if you so desire, which is the big square root of p times 1 minus p all over n. Okay. Oh, and to be fair, that's the standard error of the sample proportion. But we just abbreviate it without the sample. But it is technically sample proportion, but it's fine. All right, so let's see. Let's apply it to this problem right here. So according to a recent article, 98% of the people who travel on the New Jersey Turnpike exceed the 60-mile-per-hour speed limit. Law enforcement officials plan to covertly measure the speed of 750 cars and on the turnpike and will compute the proportion of drivers who exceed the posted speed limit. All right, seems simple enough in theory. Now, hopefully you know what the word covertly means. That means that they're going to do it in secret. So they're going to hide behind some shrubs and they're going to zap people with a radar gun and see if they're speeding or not. At least that's the theory. All right, so let's start by describing the sampling distribution of p hat. All right, for starters, it had better be normal. If it's not normally distributed, we've done something wrong for the shape. But let's prove it. We need n times p times 1 minus p to be greater than 10. Speaking of which, you know what? Let's take a moment, and just as an aside, let's make a note of a few things from the problem. And this is actually a very smart idea to do with these problems. Figure out what your n is and what your p is. So n is your sample size. So if you look around, it says it's going to measure the sample of 750 cars. Hear that right there? That's your n value, right? Okay, so n is 750. P is your chance of success, which according to the old data was 0.98. Now the 60 has nothing really to do with it. 60 is just letting you know what your mile per hour speed limit was. So it's a good idea to figure these out ahead of time. So figure these out from the paragraph first before you answer any questions. All right, now for the distribution, it's going to have a shape that is normal if n times p, which is 750, times 0.98 times 1 minus 0.98. As long as that is bigger than 10, we'll be okay. So let me grab the calculator. 750 times 0.98 times 1 minus 0. Here, let me do that again. 750, 0.98, 1 minus 0.98. My keyboard's being a little possessed there. Hold on one second. There we go. Now I got it. It's 14.7. All right, so this is 14.7, and that is bigger than 10. Yay, right? We need it to be bigger than 10, otherwise it's not going to be any good to us. So we just proved that it's bigger than 10, therefore this distribution is normal. Now the center of the distribution is 0.98 because that's what your p-value was. So that's done. And then the difficult one. So the mu is so easy, and then the sigma sub p hat is a little bit more tricky. So you need a square root, and then you need 0.98, 1 minus 0.98 over n, which was 750. All right, now I got to go find that with a calculator because I want to get a decimal approximation for this just for our purposes. So square root, so big square root, 0.98 parentheses 1 minus 0.98, close parentheses, divided by 750, enter. And I get 0.005112. And remember, we want to keep at least 6 decimal places. So 0.005112. And then make a note, keep at least 6 decimal places. If I could get it to highlight there. For the standard error. There we go, for the standard error of p hat. All right, so that's the distribution. That's lovely. So now let's answer a different question. As a matter of fact, I think I might rearrange the order of this question so that we can prove this, but that's all right. So they say, what is the minimum number of people? Well, that's a different kind of question. We haven't had that one in a while. So what they're asking us to find is, what's n? Okay, so they're asking us to find n in order to ensure that this is normal. All right. So note, we are being asked to find n such that the distribution will be normal. Okay, so we know 750 is normal, but what's the minimum number we needed? Maybe they didn't have to get 750 cars. So what we're going to do is we're going to say, all right, we want this to be greater than or equal to 10, according to the formula. So I'm going to let n be blank. I don't know what that is, but I know that p is 0.98. Then I know 1 minus 0.98, and I want that to be greater than or equal to 10. So I'm going to grab my calculator. I'm going to find what this number is. 0.98 times 1 minus 0.98. So let's see, 0.98 times, parentheses, 1 minus 0.98. I don't actually need the parentheses or the time symbol in there, but that's all right. So 0.0196. So this is n times 0.0196 is greater than or equal to 10. Now you want to solve this for n. It might have been a while since you've been in algebra class, but this operation right here is multiplication. So to undo multiplication, what you're going to do is you're going to divide. So you divide that side by 0.0196. And if you do it there, you have to do it here as well. So over here, the 0.0196 divides away to 1, so that disappears. Right? So we get n is greater than or equal to, and then I have to find this number, 10 over that second answer, 510.2. So 510.2. Now, one thing that came up when I taught this in the face-to-face classes, they thought you had to, when you divided, you have to flip the sign. But keep in mind, that's only when you divide by a negative. We're not dividing by a negative value here, so we just leave the sign as this greater than symbol right here. Now, the bigger issue here is that you can't sample 0.2 of a car. I mean, we're talking about the number of cars these cops have to zap with the radar gun, right? So they're going to have to round, and they must round up. Because if they go any lower than 510.2, it will not be normal. So we're going to make a note. Must round up in order to ensure data set is normal. You know what? Let me write that up outside 1 second. There we go. We must round up in order to ensure that the distribution is normal. So there we have it. Let's move on and do this first part right here for part C. So it says in a random sample of 750 drivers, what is the probability that more than 98.5% of them are speeding? Draw a picture, shade it appropriately, etc. So I've got the picture already drawn here. Now remember, we said that the center was 0.98. That's what we just said right here. Center is 0.98 right there. And then the spread is 0.005. So 98.5 is about 1 standard deviation away, kind of right over here. And we're looking for that area right there. Well, to find the area under a normal curve, we're going to use normal CDF. And let me remind you, I'm going to put these in the notes later, so you might as well see them now. So we want to find an area, a probability. It says, what is the probability? So therefore, you're using normal CDF, right? Left to right, P and square root of P times 1 minus P over N, i.e. the values we already found. So we're going to use normal CDF. Now the left-hand edge of what we shaded is 0.985. The right-hand edge of what we shaded is forever, so it's 1E99, comma. And you might be wondering to yourself, well, you can't really go to forever with it being proportion. That's true. However, we're finding this by using a hypothetical curve. So it's a classical curve. So we're kind of divorcing it from the reality of its situation just a little bit. So we're just going to say it goes to infinity. And then the mean was 0.98, right? And then the standard error, that's the fun one. That is the big square root. And actually, I prefer using the big square root. I use this when I type it into the calculator, the 0.98, 1 minus 0.98 over 750. And I'm going to show you why that is in a bit. Okay. So let me grab the calculator. I'm going to clear all this out just because it's making a mess. I'm going to go to second distribution, pick number 2, normal CDF. We said 0.985. 1E99, 0.98. Now I'm going to type in the big square root. Second square root, 0.98, parentheses, 1 minus 0.98, close parentheses, divided by 750. Close my other parentheses. So 0.98, 1 minus 0.98 over 750. I'm going to press enter. And then enter. And I get 1640. All right, so this is, let me put that in 1 second. Now I want to show you something. We said that 0.98, 1 minus 0.98, all that business, was about 0.005. See it right there? So I want to show you what will happen if you try to use a rounded answer. So let me go back to normal CDF, pick number 2. But instead of doing that big square root thing, I'm going to do 0.005. I just want to show you this. Press enter. Look how wrong this answer is. See how off we are? The 1640 is the correct answer. And by rounding like that, we've made a terrible mistake. Let me do it again. Second distribution. Let me say, well, 0.005, that was terrible because we had 3 decimal places in our actual value. So what about 0.0051? Enter. That's still wrong, right? Look, you're off in the hundredths place. Neither myself nor my math lab are going to accept an answer that is that wrong. So that's no good. So what if you did number 2 and then kept the 6 decimal places as I recommended? So you say 5112. It's not perfect, but it is correct up to the 5th decimal place, right? This one worked out to be 5th, sometimes they'll be 4th. But you can see that's why I say in the notes you have to keep lots of decimal places. So let me make a note of that right here. There, I made that note right there. If you round the standard error of the p-hat to less than 6 decimal places when you type in the calculator, you will be wrong. To never be wrong, just use the formula. It's simpler to just use the square root formula. With the square root. There we go. All right, let's pause right here and I'll pick back up with that percentile question in the next